It's now 6 o'clock and I should start talking about TensorFlow, I guess. And I already have a question by Nordlicht. That is definitely a German name. And the question is, TensorFlow 2 seems to be the latest version, but your video courses use TensorFlow 1. Oh, okay. So that's actually a pretty good point. So today I will be talking about TensorFlow 2, but my course came out early on March last year, where there was no TensorFlow 2, and then it might be that you think it's outdated. But since in that course, this one down here, let me scroll down a little bit, sorry, like this. So in this course down here, it's this one. I use the Keras API, that is the high-level API of TensorFlow, and this hasn't changed, or almost just very slightly has changed. So all of the stuff that you can learn in my video course still applies to TensorFlow, but at the same time, I converted all the notebooks to the TensorFlow 2, which just barely took me like half an hour, because most of the things are really quite the same. So very good question. So the question is, next question is the presentation mode in Colab? Maybe F11. I think, oh, good point. So let's see what I can do. Pretty good. Kudos to Chiroptical for having this great idea. Yes, nice, yeah, good. Also like that. As I said, this is the first time for me streaming on Twitch, so there's definitely a lot to learn for me still. Okay, so this is a notebook, and maybe you know it, but this notebook, so it means it's a mixture of text and code, and the code is executable, and the result of the fractions of code that you execute will be displayed directly in the notebook. Okay, so there's some more chat. Also check out Chris Medman's guest stream. So Chris Medman obviously explained why TensorFlow 1.x is still relevant. And I guess it is. I'm not quite sure why Chris thinks so, but I would think so that a lot of deployed models are still on TensorFlow 1. But as I said, all the stuff that you can learn in my course, it's basically the same API, because I use the high-level API. So today, because now TensorFlow 2 is there, we can take a different approach, namely we look at the low-level API of TensorFlow 2, and from there work our way up to the high-level API. So this means even if you know the course, or if you still want to watch the course, this could still be pretty useful, because there's barely any intersection. Okay, so I get distracted by the chat, and I like this, but I try to stick to my red thread here. So this is the notebook that I'm showing you. So if you, I don't know, take a screenshot, or if you're fast, you can type it into your machine, and then you would see the same thing that I'm seeing. So the Colab notebook obviously now is in presentation mode, which is nice, but you can just follow along if you want to. So this is the video course. With this thing, you get 40% off. Oops, I didn't mean to do that. Keep doing this. You can follow me on Twitter if you're in that notebook. My Twitter handle is DJ Korthose, which means something in German. It's a special sort of pants. And as I said in the beginning, I converted all of the notebooks that we had in the course. I converted them to TensorFlow 2, and there's a GitHub repository that contains the old TensorFlow notebooks and also the new ones. There will be more content on the Manning channel, and you can have a look at it. Well, obviously you're now on the Manning channel, a little bit to the left, a little bit down to the stream. You see what else is going to happen this month and later. One more question. Okay. Oh, and I see that, okay. Now I see that Manning Publication is saying that you can win a free ebook. Oh, okay. I see. Okay, all cool. Good. So let's go through that notebook. As I said, it's a mixture of code and then not only code, but you can execute the code. I'm doing it now. This is just basic setup of like how big will the graphics be. And what I brought with me is this example. So this is something that we're obviously trying to use machine learning on. And each of these blue points, it's just a sample, a data point, so to speak. And you have this X and Y axis. And typically, it's very hard to associate this to something in your real life, unless I make you think about it a little bit. What could this be in your daily life? So what could be those data points? What could be on the X and the Y axis? What could this actually depict? What could this be? And I need you to help me a little bit with this. So I need something in the chat maybe that you propose something what those data points could mean and what they are like displaying. I know that there's a little bit of lag between the chat and the stream, so I need to wait for a few seconds. Let's see. So while you're answering, I can also have a look at the chat. So is the matplotlib pragma required? I'm scrolling up. It's not. This is just because I also make this run on my local machine. What else? Okay, so no, it's not required. Oh, okay, there's something coming up. And Telecommander says account balance in in quarantine. That's quite funny. I thought that we might find something that's associated to the coronavirus, so it might be. So that would mean X would be time and Y would be account balance, I guess. And I think that's a pretty good thing, and I think we can already just keep that. Why not? Why not stick to this? So this would mean so the y-axis would be count balance. Unfortunately, it's going down. X label would be, let's say, time or days in quarantine, and just calling the whole thing account balance. And as you see, there's some nice features in this Code notebook. So you get this like sophisticated kind of UI, but actually when you click into it, sorry, I didn't mean to do this, what I just did. Oh, that was a horrible thing to do. I just messed it up. Try to do something else. Let's see if I can get it fixed. There's some code behind, and this is just normal code, just Python code, but it's annotated with this kind of stuff. So some parameters. And when you do this, you get this view here as well. Not quite sure what my n used to be. I think it was 100. But I'm also not too sure that it really matters. So this 100 is actually how many data points do we want? And once you change that, this thing gets re-rendered. And it still looks okay, so I think we should be all good. Let's see. There's more examples. Yeah. So someone has said that it seems pretty useful for teaching. It is. And it's also very nice to interactively try something else. I also use it if I'm not teaching something, but if I just want to try out different parameters, that's very nice. So as I said, if I change this, for example, you see it's redrawing. You can't see it too much because I removed the scales on the axis, but it does things. And I need to put it back to 1, otherwise I'm confused later. So this is the slope of the thing. No, it's -1, okay. And you see once I do this, it gets redrawn automatically. So that's quite nice. Does it work in regular Jupyter notebooks, chiropractical? No, unfortunately not. That's a pity, but there's some things that work better in typical Jupyter notebooks and some things that work better in Colab. And this is one of the things that only unfortunately works in Colab. That's a pity. So there's something else by Nordlicht. Maybe why is satisfaction or happiness Okay, and that's also quite nice. So on the y-axis, Nordlicht says it could be satisfaction or happiness, and on the x-axis, it could be how long a website needs for loading. And I think that makes a lot of sense. The longer you have to wait, the less happy you are. Also quite nice. So if you have another example in your head, the machine learning approach that we're using, it doesn't mind too much, because it just looks at the data points and it doesn't need to have any idea of the domain. Okay, so that's what we are having. Now, I think you already know that what we're trying to do now is we're trying to fit a line through this thing. So we want to know how does it go on like tomorrow? Like after the data points that we have, how does it continue? And typically this would be a linear regression. There's well-proven methods to solve this. Typically you wouldn't use something like a neural network to do it. But our point here is to explain how neural networks work or not to solve this thing actually. So first of all, we make the assumption that this actually is a line. We don't have to do that, but I know the way I generate this thing, it's actually a line. But we can put it into our model. That means like into our assumptions or not. First, we put it into our assumptions. So this is our model for this line, and this is the output y. Sorry, this is the account balance. X is the time. This is the slope, and b is the y-intercept. Well, that's where the line that we're thinking of, where does it like hit the y-axis. And the slope is like how steep is it. So there are two parameters. That's very easy to do in Python. Disregard the rest, don't look at the other stuff. This is the important line here. And you see, I just write it down in Python. Job done. Execute this. This is the input data points. This is like the timestamps. And now I can put those timestamps into our model. That's what I'm doing here. And I can plot the output. Let's see. And you still see that the original data points, they're still here, the blue ones. But the predictions of our model, it's the red one, it's totally off. So obviously. So it is totally off because we just set the slope to 0, we set the y-intercept to 0, and that's what it's doing now. It just draws a straight line like this. And that's not what we want. So the first thing that we should do is like quantify it. How wrong are we? And there's different ways of doing it. And first of all, like the most obvious thing that you could do is like you take the difference between the true value and the predicted value, and you do it for all the data points and you sum that up. That means if you look at this data point here, this is the true one, the blue one, and the red one is the prediction. And now we are taking the difference between these, and we do it for all data points, and we sum that up. And then we have like any measure for how bad we are doing. It's not speaking to us. That means it's just a number. But that's the first thing we can do. Unfortunately, it comes with a problem because this difference can sometimes be negative and sometimes be positive. So in the next step that we're taking, we take the absolute value. So let's execute this. So, and you see that the absolute value is a little bit different because sometimes the positive and negative ones, they cancel out each other. And now this looks pretty high. If you look at the scales, this is between 0 and 1, and they're saying the total like error is 55, but it should be rather between 0 and 1. So what we're doing in the next step here is that we are dividing the sum of errors by the number of data points we're having. So let's do that. And now we're around 0.54, which still is a very bad value, but at least it's a little bit more intuitive. There seems to be a question. So Mr. Demon Wolf is saying, Python is surprisingly good for this kind of data. It's hard to understand this, but I see why it is used. I would not necessarily do it like this in Python. It's pretty simple to do it like this in Python, but this is just to make a point clear how you could potentially do it. So if this was your real challenge, you probably wouldn't do it like this, but you could. And yes, Python is quite nice. You could do it in R, and I don't think there will be a lot of differences. So now we have a measure of how bad we are, and this is again just a number, but you could look at it like the average, like how wrong is each data point on average. Now what we're trying to do is bring down the loss, like this number. We want to bring it down to 0, like it should be a perfect fit. We can't reach that, but this is our goal. And what we can tweak to bring it down is the slope of this line. Again, scrolling up, this is the line, the slope is 0. We can change the slope, so it should go down like this. And also the y-intercept should be different. Obviously, it shouldn't be like hitting the y-axis here, it should be hitting it somewhere else. So those are the 2 parameters we are tweaking. Let's see. And I decided to first do a very naive implementation. And this is how it looks like. So we just try it out. It's a little bit like brute force. So we bring M up and then B up, and then we see, does this improve the loss? And if it does, we're committing to it. And if it doesn't improve the loss, we are reversing it. So we are not bringing it up, but it's dead down. And this is what we're doing for like a certain number of times. And this certain number of times is called epochs. Or I call it epochs. Well, everyone calls it epochs, but it could be named whatever. So I'm just doing it for a number of times. And then how far I bring each of these parameters up or down, I call a learning rate. And that's also something that you will find later again. And while I do it in this for loop here, this one, that's how you could do a for loop in Python. I stick in all the data, calculate the prediction, use this loss function that we just created, append that loss function to a predefined area up here, or list, better to say, just to keep it. And then I'm trying to bring M up by the specified learning rate. I'm recalculating the loss, and if the new loss is lower than the previous loss, I'm committing to it. And if not, I'm reversing my decision. And then same thing for B. That is the y-intercept. And that is it. It's a very naive implementation, so you wouldn't use it practically, but this is just to get my point across. I'm running it 500 iterations, that's pretty fast. So the slope that I calculated is minus 0.9, and the y-intercept is minus 0.96. I know it should be minus 1 and 1, but well, it's hard for this thing to actually find out the right line because it's so noisy. And we can look at the loss over time, like how did we do over the time. And you see it goes down at the beginning quite a bit, and then nothing much happens anymore because we're pretty much as good as it gets. And this is pretty promising because it might tell us that we actually now have this line fitting the data. And if you look at it, it works surprisingly well. I mean, the code is very naive, but it just works. So it's already a working implementation, which is quite nice, right? We do something naive, it works. So far, this isn't TensorFlow. So far, this is just the basic idea of fitting data. You have a loss. You try to bring that loss down by a certain strategy, and then there you are. Okay, so now we already have a working solution, but it might be a little bit harder if we have a lot of parameters, not just one. So in real life, it can be much harder. And then also, we are not trying combinations of each of those parameters. So we're not trying to bring up both the the slope and y-intercept at the same time. So there might be issues to it. And that's a question by Prime Play Master. Okay, someone is asking if I have other socials where they can watch tutorials. Yeah, I will post some stuff later. So as I said in the beginning, there's a video course. Also have stuff that I mostly post on Twitter. Maybe I can post on my Twitter handle. It's a little bit of a challenge. I guess I can do it. So my Twitter handle is the same as my, Twitter handle is the same as my Twitch handle. I just realized this. So yeah, and I'm posting regular stuff, or posting stuff regularly. So there's something else. Ryan Mark 24 says, great way to show things from the ground up, really clear and concrete. Thanks a lot. Thanks a lot. I really very much depend on your feedback, because I'm just talking to the void more or less. So, and also if something is not clear, or if I should change something, just tell me. Okay, cool. Now we're going into the TensorFlow part. So what we're doing now is that we are replacing our model, which was a very, very simple model, just 2 parameters. We're replacing it with neural networks. So this is how you get access to the TensorFlow 2 version. You have to do this. I'm not quite sure if you still have to do this, because at a certain point, they switched the default version of TensorFlow to TensorFlow 2 on the Colab. Not quite sure if you still need to do it, but that's the safe way. So this is how you ask for the TensorFlow 2 version. I'm importing it and ask, okay, which version do we actually have? And this is 2.2. One of the drawbacks, not a real drawback, but one of the specialties of Colab is that you typically also get all the release candidates, and sometimes they're a little bit broken. And I'm hoping that this release candidate works well. I'm not quite sure. I tried it a little bit earlier today, but I think it was the same one. It should be fine. What I'm also doing is there's a lot of random stuff going on. I try to spare myself as many surprises as possible. So you can set a random seed, which makes all this stuff reproducible. And of course, 42 is the only valid random seed you can set. Oh, and I see Hardware One says he has RC4. So there you go. So maybe they fixed something in RC4, maybe they broke something. So a little bit like that, not really beta tester, but you're a little bit a tester. So what Colab gives you, which is one of the reasons I like it so much, is that you get a free GPU. Free means you don't have to pay for it. And in my case, it's even a P100. I looked it up the other day, and I think it's $2,000, $3,000. So that's a decent one. You probably get a different one, because a little bit depends on luck. And then I also paid a little money to have the Colab Pro thing, so maybe I get the better GPU. But this is a really decent one, and it's a little bit like how do you say pearls before swines? That's what we say in German. That means we have a very simple task to do, and I have a very, very powerful GPU. So probably, but you still get that. Okay, so the first step, now we have a GPU in place, we have TensorFlow in place. So now we are modifying our model. And the first step that we're doing is, instead of the model like we had it, we're using a so-called dense layer. Let's see what this is all about. So actually, if you understand this picture, you will also understand what a dense layer is. There might be a question. So to make me sandwich, I like this. GPU flex, cool. Okay, so let me see. So this is an image of an artificial neuron. This thing has been invented, if you want to say so, I guess in the 1950s, and it's inspired by the way people thought at that time how neurons work in our brain. This is not quite up to date now, so people think neurons work differently, but let's still have a look at it. Namely, so you have a number of inputs. In this case, we have x, y, x2, x3. So this is 3 inputs to make it a little bit more exciting. In our example, we have just 1. Now, each input is multiplied by a weight that's associated with that input. And in our example, x1 is 10, the weight is 1.5. We have x2, weight is -2. We have x3, and the weight is 1. And then you multiply each of those, and then you sum them up. So this is the sum symbol here. That means this is the calculation that is taking place. So this is 10 times 1.5 plus 6 times -2, and so on. But you also add a so-called bias, the 6 here. So it could be something else. This just happens to be the configuration of the neuron. So those weights, weight 1, 2, 3, and the bias, those are the parameters of this one neuron. Typically, you don't have one neuron, but maybe, I don't know, 1,000, maybe a million would be a lot, but it's still possible. But at this point, we're just dealing with one. So then you sum that up, and this is the result. So each neuron has one output and is always numerical. So if your data is not numerical, you need to do something to make it numerical. In our case, that's easy. We just have one input, namely a 1x and the 1y. Cool. So let's do that. This is, again, something very similar as we had before. So I'm defining a Python class that's a TensorFlow layer, but this is not important. So the important part is down here. Again, what does this thing do? And this just uses one of those neurons, the one neuron that I showed you above. And maybe you saw it, but this operation that I was showing actually is a matrix multiplication, can be expressed as a matrix multiplication. So TensorFlow low level gives us this matrix multiplication, and it says whatever weights you have, whatever inputs, I'm doing a matrix multiplication and adding the bias, which again is pretty much the same as we had before. But this time we replaced the mathematics operations with something done in TensorFlow. This also means this will now run on a very powerful GPU. This simple operation, very powerful GPU, but we can still do it. So it's the same thing as before. So I'm making a prediction, and it does the same thing, but obviously it's also, because I didn't do anything to those parameters, it's also totally off, totally wrong. And it's because those parameters have been initialized randomly. Let's see, what are they? So the slope is 0.65 and the y-intercept is 0. And you probably already understand that if I go up, that the y-intercept is this b, and the slope, if I just have one parameter, is this weight. And that's quite nice. So you might already understand that an artificial neuron like this can express a line or linear function. That would mean, like in higher dimension, it would be hyperplane, but it's still linear. So we only get a line out of this, which is interesting, right? Now, next step, we are replacing our loss with a different loss. And this loss that we're using, so the loss is like finding out how wrong are we. And what we're using here is called mean squared error. That means we are also subtracting the predicted value, which is this one, from the real value, and we are summing it up and we are dividing it by the number of samples, so pretty close to what we had, but this time we are squaring it. So we're not taking the absolute value, but we are squaring it. And this means larger errors get more emphasis because they are now squared and they get a little bit larger, so there you go. Okay, cool, so that's what we're doing. There is a predefined version of that from TensorFlow losses. Just use the mean squared error. I put in the true values and the predicted values, and I do a little bit of magic around it, and then I get the loss, which is this. Unfortunately, this thing is still not speaking. So even though TensorFlow will try to optimize this thing, we're actually looking for something else. And this is also very common in machine learning. Namely, we look at something that's more speaking. That is an R2 or R square metric. And I implemented it myself. There should be a version somewhere, maybe coming sometime. It doesn't matter how very much like how I did it. It's more interesting like what it says. So the closer it is to 1, this score that calculates, the better it is. If it is 1, it's a perfect match. If it is 0, then it would be like as good as predicting the average all the time. There could be negative values. That means it's really, really wrong, extremely wrong. Typically, you get a value between 0 and 1. And 0 would mean not so good, and 1 would mean pretty good. So let's see. So in this case, we get a negative value. That means that's worse than it's like super worse. It's like super bad. You see, it's super bad because it's pointing in the wrong direction. So in certain optimization like strategies like ordinary least squares, this would be an impossible solution anyway. So it's really not good. Sorry, I just needed to check the time. So we're using this one. Oh, sorry, I scrolled in the wrong direction. So we're using this one, and now we have this as a measure of like how well we are doing. And if we are closer to 1, we should be okay. Now what we're doing, we use the so-called backpropagation algorithm. Typically, you don't need to like know it in detail if you're starting with neural networks, but it can always be helpful to understand what's going on under the hood. And we make it really short. So how does it work? So first you do a prediction. That's what we did before. So we stick in all the data we have, you get the output, we calculate the loss. Also what we did before. Now something magically happens. And that means while we're predicting the loss, we track the dependencies between the parameters and the input. And we don't have to do it manually. It's something that TensorFlow provides us with. And from this tracking, we can find partial derivations. That means like how much did each of those parameters influence the loss, more or less, like loosely speaking. And then in the final step, a certain algorithm uses this data and finds out which parameters to tweak. And that's it. And that's very close to what we were doing before. Let's skip this for a second. Let's also skip this. Just take my word on it that, well, maybe we're looking at it very briefly. Just take my word for it that TensorFlow can track dependencies with a statement like this. So it's saying, please tape everything that happens inside of this. So if you're doing an operation like this, it will know how y is dependent on x. And then you can later get the gradient. That means if you understand a little bit of calculus, that means like how much, like how big is the influence of x in y. And you don't have to do it. It's built into TensorFlow. So if you're using something like PyTorch, it would be the same thing. Okay, so now we return to where we started from. We had a very naive loop, and we're now making some very, very tiny tweaks to this naive loop that we used in the first place to solve this thing. We again have epochs. We again have a learning rate. We have a list where we store the subsequent values of losses and the R squares. Because R squares are now new, we have a second metric or second measure. Let's see what we're doing in it. So we're recording this block. That means we will find out like how is the loss influenced by the parameters of this neuron, more or less, that we're using here, when we stick in x and get back y. And this is done by the magic of this thing. Just put this in a block and it will work for you. So again, like we did before, we append the loss to a list of losses. We append the R square by, well, we're calculating it. We are not calculating the R square in this block up here because we don't need it. And it will take some memory, so we don't do that. We're getting the gradients. That means like how much do the slope and the intercept, how much do they influence the loss? And then depending on like how much they influence it, we subtract from the current slope and y-intercept, we subtract like the amount how they influence it multiplied by the learning rate. So let's do that. Okay, so it takes some time because we're doing it 1500 times, but oh, it's done, so it's not too slow. So let's have a look at the losses. And this is something you always look for, that the loss is going down like this very smoothly. And this looks like a good training, and we can have a look at the R square score. And this is going up, and it's definitely over 0.5, and it's approaching 1. So we can also can have good hopes that this is a good fit. It looks a little bit different than the other fitted line because there is no perfect line. All of those are bad, and then you can never get a perfect line. So it's just a different solution for this thing. Okay, now the final thing. We're not going into details, but one thing that's still not very good is this part down here. So we just like very brute force way, we are changing all of those parameters. There could be a lot of them, and maybe you don't want to change all of them. And then also we have a fixed learning rate. Maybe sometimes we want to go slow, sometimes we want to go fast. So we replace that as well with standard optimizers. And if you really want to know how they work, you will go into, or you could go into this and you will understand. We will use an optimizer called stochastic gradient descent, which will not consider all of the parameters to see what is a good update, but only some. It has a fixed learning rate, but there are more sophisticated algorithms that also have a learning rate that is adaptive. That means depending on how the training goes, it will do either this or that. So this is the final change. We have this optimizer now. Now the loop is exactly the same apart from this last line here. And this looks a little bit strange. This is just the way, this zip thing is just a way for Python to like in a zipper, bring in the gradient, like the steepness and the trainable weight, to let the optimizer know what it should do. Don't bother too much. So we can also execute this. And probably for this example, because we just have 2 parameters, there should be no benefit. Maybe it's even a little bit slower or gives worse results. But for a larger example, this is what you would use. Otherwise, it will be too slow. So this again is the loss, how it goes down over time. R square tells us how good is this thing. It was really bad at the beginning and got a little bit better. And there you have the line. So maybe the surprising thing, let's see if I can bring it into, yes, on one screen. So the surprising thing is that this thing that you see, that is pretty much state-of-the-art low-level TensorFlow code. If you looked at like the stars, like François Chollet or other people who built larger parts of the Keras API, larger parts of TensorFlow, it will be very close to what they would write. And this is very surprising because we are, at least for me, well, it's not because I saw it several times, but I'm still amazed because we started with this very, very simple stuff, something very naive. We did a few replacements here and there. We added this tape thing. But this is the loop that will more or less train pretty much any network, more or less. And this is quite amazing, I would say. And this is a low-level thing. We started from lower level this time, not from the high level. So you know what's going on under the hood. Now we've done that, we can like take a step back. I'm actually doing it here. I took a step back and look at high-level stuff. Let's see. Okay. So we're doing the same thing, with the Keras high-level API. So this is a slide I took from actually François Chole, who did a talk about like the future of Keras. So I'm talking about Keras, I'm talking about TensorFlow. How do they relate? So TensorFlow is the low-level layer that interfaces operations like matrix multiplications mainly to CPU, GPU, or TPU. And on top of that, we have Keras, because maybe you don't want to write a loop like this all of the time, or you don't understand the details and you just copy-paste. And instead of copy-pasting, what Keras does is it gives you a declarative way of just saying what kind of network do you want. And then under the hood, the same loops run, but it's hidden from you because you don't want to see it. Because why would you want to see it? You only want to see it when you want to understand how it works, or if you want to tweak it. Okay. And this is the same thing as before. So now we are going into those Keras layers, and we're getting a dense layer. Maybe you remember that we had this fully connected thing before. Dense layer is the same thing. And in this case, because I'm saying this layer of neurons is just one neuron and one input, we're having exactly the same model as we had before. So it could be a more complex network because it's saying that's a sequential thing, something follows another thing, but we have one input and one neuron and one output. So this is as simple as it gets. So we just declare what we want. You can get a summary. That means it tells us we have two parameters, namely the slope and the y-intercept done. There we are. And now we can, there's this one step that's called compile. That means this model is associated with a loss function, which is again mean squared error. It's associated with an optimizer, like we had in this low-level thing. It's again stochastic gradient descent. It has the same learning rate, and we're also supplying an additional metric because we want to see how does the R-square score change over time. And once we have done this, we fit this. Well, fit means like fit the model to data, which is the same thing as we did in the loop. So we're passing in the x, the y. We're saying how many epochs. I think before maybe at 1500, and this verbose thing just says don't talk too much while you're doing it. This time directive up here measures the time it takes. Just putting it there so when I execute the notebook, I know that I can expect this to take a few seconds. So this is done now. And under the hood, it executed the same kind of training loop as before, but you're not seeing it. You're just supplying the really important information, like what loss function, what optimizer, what data, get the job done. So apart from the fit function, there's an evaluate function, and this one gives us, let's see, the R-square score doesn't look good. Give me a second. Maybe I made a mistake here. Or maybe the training didn't work well, which is also possible. This takes quite a while. Oh. So the R-square score, I implemented it myself, the R-square. Maybe there's an issue with it. Let's have a look. So this is loss function going down, R-square actually going up. So I'm not quite sure why this thing gave us strange values, but the R-square also looks good. So we can expect this to have a good result, and this is the result. And it looks a little bit different from all the other fittings because there are different solutions to it, and they will come up with different solutions. So if I make this run again, the solution will look a little bit different. So just to briefly recapitulate, this thing plus this thing does more or less the same thing as the training loop, but it hides it from us, so we can't get it wrong. If you're writing a training loop like the thing above, you really need to do what you're doing. You can make so many mistakes. Then it either doesn't perform well or it doesn't do the thing that you actually think it does. Okay, but you now know what happens under the hood. It's not too complex. Now from that, we're taking the next step. Before that, I need to have a look at my clock. That's still cool. So the next step that we're doing, we make the neural network more complex. And it turns out that you can prove if you add, we'll come to layers in a second. If you make the network more complex, you can prove that it can approximate any function. That means whatever function you have a neural network, that neural network can almost do the thing that the function does. Okay, but what does it mean? So first of all, a layer like this on the left side consists of a number of neurons. So in each of those squares here would be one neuron. This would be a layer of 4 neurons, 2 neurons. I'm quite sure, I think this is 6. And now an architecture, something that's more complex, would put these neurons into a sequence like this. Oh, sorry, those layers into a sequence. That would be a sequential model. But if you have something like it skips this thing, this residual thing here, or this one, then it's no longer sequential, then it's a more complex model. But this is something you can define. You need to know what you're doing if you do something like this, but you're free to do that. So TensorFlow lets you do it. And then once you train that, all the so far just random parameters of these neurons in those layers in that architecture will get assigned specific values. And this is what happens after training. So a trained model has the same architecture as this thing, but now the numbers that are in here, they're no longer random. And that's a trained model. And that's what we're doing. So now what we are doing is we have, let me count, 4 layers. First layer, second layer, third layer, fourth layer. And we are for now disregarding this activation thing. And this would mean this first thing would be something like this, and then this, and they're all after each other. First one, second one, third one, fourth one. So our model doesn't quite match this thing, but this is how we put these layers behind each other. So we're on a different level of complexity. We still have one input. So this is like totally overkill. And we have 100 neurons here. In the next layer also 100 and also 100. And then in the final layer we have just one that combines all the information from these neurons. Same thing, same model. So we configured it differently, but we still have the same loss function, the same error. We have the same metric, but we're now using an optimizer that is a little bit more sophisticated, but you can also use the optimizer we used before. This optimizer is the default optimizer that you use when you have no reason not to use it. It's called Alan, and it learns what's a good learning rate. It learns like which parameters it optimizes. It's pretty nifty. It's pretty nice. So let's use this model now. We see with this very simple model we have 20,000 parameters already, and I trained models like that had 500 million of parameters. And you see, it doesn't take much longer, right? So I think the thing before took 9 seconds, now we are on 11 seconds because this GPU that we're using has a high degree of parallel execution. That means this thing is as hard as the thing before because it can use parallel execution here, which is quite nice. That means we trained, now actually optimized or changed 20,000 parameters. And with the original approach that we had, where we try each of them and then do it for a long time, it would take forever. But this is still pretty fast. So let's see. Also the R-square score looks bad, but it could be my implementation. So let's see. Loss is going down. R-square is going up, so it's all fine. Need to check the implementation really. This is now the curve that we're fitting. So the red one is the fitted curve, and you see it's no longer a line. You see it up here, so it's a little bit wiggly around here because it's so okay. If I do it a little bit more like this, I get a better score. So down here, it still looks pretty much like a line, but not really. And this is because we lifted the restriction on the model that it can only use, or it has to approximate a line. That might be desirable if you really know, okay, I want a line, But in this case, we were saying, no, we don't want a line. We want whatever fits best. This is quite interesting because some people say, okay, will a neural network, like how much information do you have to give it to fit your data? In this case, I gave no restrictions. I made the model extremely, like ridiculously large. So it had all the possibilities to fit something that's really strange, like, I don't know, wiggling up and down and wiggling up and down, but it doesn't do it. Because it sees, okay, this is the best way of fitting it. And in this part, it was a line, and this part, maybe not so much. So we were lifting the restriction that the model needs to be in line. Sometimes it's helpful to give that restriction when you're really sure it has to be in line, then you can give it, but sometimes not. Which brings us to the second example, which is not a line. Let's have a look. Namely, it's a sinus curve. And it's again noisy. And you still see that trick, right? Number of points that I'm generating. This is the noise level. This is the scale of the thing. And you see it looks a little bit like a sinus, but because the noise level is quite high, there's a noise level. It doesn't exactly look like a sinus. I'm not quite sure what I need to execute here to have this thing, but I think it should be. Let's do it again. Oops. Oh, not quite sure what happens. Sorry. Okay. I'm executing this thing. Okay, fine. Now I'm using the same network as I had before. So 4 layers, but I'm fitting different data, namely this sinus data. And I think all the other stuff is exactly the same. It should take approximately the same amount of time, namely 10 seconds. Let's see. Oh, it's pretty fast. Maybe you had less data points, so just 7 seconds. Disregard the R-square score. Well, in this case, it works. So it looks really good. So something very close to 1 means it almost fitted the sine wave perfectly. Let's see how it did it. And now you see that the blue ones are actually is the real data, and the red ones is how the network learned the data. And you can always say, okay, obviously this network learned the data points by heart, which is in a sense true. And like how you make sure that it's just not learning all these things by heart, and then how you make sure that it also applies to data or to predictions that it has never seen before, something that's handled in my course. Like how do you make it generalizable for unknown data? Also something, now we are already at the end of this. Also something that we did not look into is like, in this case, we were predicting a second value that is continuous, but often you want to make a prediction, is it either this or that? Is it a dog or is it a cat? This is called classification. There's a second notebook, which we don't have time to go through today, just have it as a reference here. In this one, we're using very, very similar networks, one or more additional tricks to actually also predict a category. This is also something like a prequel to the video course. That means that's also something that you can look at, and you will learn something new in the video course. Okay, so that's the video course. You can get 40% off, obviously on all products. Okay, I just checked it on this video course, so I guess it works, but try it. And I did something like a special thing. Maybe you just briefly click on it because we might have maybe a few more minutes. Let me have a look. And because I thought maybe we will not come up with a very good example, but we did. So the example we are finding very good. So I did this for the corona cases in Germany. And let's see. So it's again a sequence of data points. Let's have a look. Sorry. It's a lot of stuff. Sorry. Okay, so this is the sequence of data points. And you see, it's not really a line, I would say. So this is like daily accurate data. This is the number of cases in Germany. And you see, it's not a line, so we will probably not be able to fit a line through it. But I still did. I did this very same thing as we did in the example, and I fitted a line through it. Let's see. There's my line. Bear with me for a second. And these plots of the loss, you're familiar with. The loss goes down. The R square, where's the R square? I think I'm not plotting it. And now, my R square score is pretty high, but this is the line that we are fitting through on this curve. We're seeing the line just doesn't cut it, because this curve obviously is not a line. And for someone who has looked at lines this curvy thing, this blue thing before, you see that this saturation curve, it's an S curve. And now you can tell the network, okay, instead of like fitting a line, fit either any network or fit a saturation curve. And I did the S curve thing. Let's have a look. Oops. Oh, I'm sorry. Scrolled too fast. Oh, where is it? Okay, this is the S curve. And no surprise, it fits extremely well. Because this thing actually, I mean, I should not say it, but I'm saying this thing actually is an S curve. Because it's in saturation curve, that's just how the world works. Now I'm doing something I should never do, namely make a prediction for the next 10 days. Let's have a look. Oops, that prediction looks horrible. Oh, I messed it up in a way. Oh, this is really strange. I should, give me a second. I think I executed it before. Oh, that's horrible what I did. Sorry, I'm rerunning it. That's really not good. So maybe this is what higher forces made, namely that I'm not showing the prediction. Not quite sure what happened. It's really strange. Maybe there's a bug somewhere, but I'm not showing the prediction. Instead, I'm showing a different result. Maybe this thing works. I did it today. Maybe I did it in a hurry. I think this thing now. So this thing now is trained on a recurrent neural network. We have a different section of the data. So we're not having the initial part of the curve, because this thing always needs like 30 days in advance before it can make its first prediction. So this doesn't look like a saturation curve because this part of the curve is missing here. And now where you see the blue line, this curve is actually applied on data, on input data it has never seen before. So it has only been trained up to this point, and from this point it makes a prediction, this dotted red line. And you see the true values because we also know them, because they are 5 days in the past. And you can compare the real values, namely the green ones, to the predicted values. So this is quite nice because the model has never seen those values. And this is a little bit of like a validation of your model, because you now see it also works on data that you have not seen before. Cool. So with this, I'm closing it again. If you're interested in my video course, go there. If you want to follow me on Twitter, go here. Ask me questions. My direct messages on Twitter are open. And with that, I'm open for a question or two. I almost used up my hour. Are there questions, actually? Something in the chat. So Telecommander is saying, okay, I have a basic question about inputs and outputs. Let's say the coordinates are the trial of stuff when I come home from work. Oh no, don't type too fast. When I come home from work and make my way through the house, the location of my shoes, my socks, my wallet. And the next day I miss my keys and I want it to predict where possibly. Oh, cool. So this actually sounds like the final way I used the prediction for the corona cases. So you're sticking in like a sequence of things, which we also have here. And this would be a recurrent neural network. And then it will learn what's your typical sequence of like where do you usually go. And then based on like a fraction of those places that you go, it will predict maybe the next one or where your keys are. So this would be a recurrent neural network. So telecommander says again, so basically predict the possible next point in sequence. Yes, this is recurrent neural network. So more questions. How do I tell the model I want the next point or maybe points based on the ones I fed in? Yes, this requires a specific style of pre-processing of your data, namely cutting it into slices, and then taking a certain number of like past events, say 5. This is a little bit, maybe it's not very comprehensible like I explained it, but you're cutting your sequence into parts, and from the past parts you predict the next one. If you really want to know, look into the Corona notebook, because that's what I do there. Maybe I'll show you the code, maybe that helps, because I didn't explain it well. I noticed it while I did. This is the code that splits my sequence into chunks for the training. That's what you also have to do. Okay, so Nordlicht is saying this was pretty low level and contained quite a lot of math. True. Okay, good question. We'll need some more math skills for the full course. Okay, so for the video course, there will be no additional math, but even less math. So in this course, you saw a little bit of calculus. We were talking about partial derivatives, and it might scare you, but you actually don't have to know all that. You can also just work on the high-level Keras API, and it will hide all that from you. And it will also bring you like very far, even without really understanding. In the course, I do this exclusively. So there's basically no math in the course. Okay, telecommander also tells me, I will look at the code, that will help. You can also just copy paste the code like we all good programmers do. I also adapted it from somewhere else. This is one of the dark secrets of, maybe it's not a dark secret, maybe it's not even a secret. This is something like almost all all successful programmers I know, we take code from somewhere, we change it a little bit, and try to make it work. Otherwise, writing everything from scratch, a very hard thing to do. Okay, so just take it. I put some reference to someone else who provided the original version. I extended it. Telecommander will give us the next version, I guess. Maybe on Stack Overflow. Okay. Nordlicht says, okay, fine. Thank you, Nordlicht. Are there more questions? Maybe one more question. Anything else? Hardword1 says, thanks. Thank you, Hardword1. Oh, thanks for providing the code. Yes. As I said, that's how we do it. Someone provides it to me, I change it, I provide it to you. I'm looking at the chat down there, that's one. So Hardware is also asking, what was the most interesting finding through ML so far? Like my most interesting finding through ML? Okay, yes, if you can disclose it. So let's see. So maybe that's not a good answer, but typically in machine learning, you often don't learn too much, but have a model that does something reasonable. So you often don't understand what it is doing and why it is doing it, but it's useful. So typically the interesting findings come through something I would rather call data science, namely looking at plots, maybe using a little bit of machine learning to find something out about something. Having said that, what was the most interesting finding? So I think, yes. So I trained a reinforcement learning model, which is also based on neural networks. And it was very interesting to see that without giving it a very, very coarse description of a problem, it was able to figure out solutions. That was pretty exciting. Looking at data, you often find correlations that are really interesting between things you have never guessed, sometimes things that probably, I don't know, looks like fraud or something. That might be interesting but scary. But there's nothing where I could say I found out great things, unfortunately. I know some people try to predict stock market courses. Don't try that. It's much harder than predicting the cause of coronavirus, because there's so many influencing factors you have no idea of. And if you don't know, if you don't stick in all those parameters into your model, and the model can learn all these parameters, basically learn how the world works, something like predicting stock market courses will not work. But maybe I'm just lying to keep you away from that thing so I can take all the money, but I'm not. No. Okay, so no more questions popped up while I was still talking. So with that, finally, I will give you one last time. I will give you the link to this notebook, which also contains all the other links. I guess this was recorded as far as I know. So if you want to just have the notebook or just go to the course, you can do that. Okay, thank you so much. So I guess I will stop broadcasting if I find the right buttons. It's the same thing as the thing with the Zoom calls. You say goodbye and then you don't find the door. Let me have a look. That's pretty small. I think I found the button now. I'm waving now. Thanks a lot for attending. If you have more questions, ask them on probably Twitter. So thanks for tuning in, and goodbye. Have a nice day.